Today we will begin our study on the first chapter of engineering geology, the minerals and rocks. This chapter will be the basement of all the knowledge of engineering geology. So, okay, we will start from the mineralogy. Actually, the crust of our Earth is composed of three major rock types, and this chapter will traces the origin of the three types of rocks, and which will provide the classification of the rock groups and the description of the rock types under each group. And it will further provide an account of the various minerals, including their physical properties and crystal forms. Maybe you already heard the word minerals for many times. Minerals are the solid uh, constituents of all rocks, including igneous rock, sedimentary rock, and metamorphic rocks. And occurred as crystals in of these rocks. And this term, the mineralogy, is a science or subject of the minerals. So all rocks are composed of minerals which are homogeneous substance with fixed chemical composition, crystal forms, and some other distinctive characteristics such as color, luster, and hardness. So, to put it another way, mineral is a substance that is naturally present in the earth, and it is not formed from animal or vegetable matter. For example, the gold, silver, and salt. Here are the three types of minerals: gold, copper, and pyrite. And these minerals are very popular in the past and present in on our Earth. And yeah, you must be familiar with the gold, which is very valuable, and everybody wants it. And the pyrite is kind of minerals which has another name of fool's gold because it looks like the gold nugget. And it is a very common brass yellow mineral, and mm, it is often burned to sulfur dioxide in the manufacture of sulfuric acid. So it often resulting some decreasing of rock strength during the uh, mineral composition in the rocks. A mineral is composed of atoms arranged in a very oddly three-dimensional structured crystalline. So I'm sure you have already studied some knowledge about the uh, studied in your um, high school chemistry. For example, the highlight and quartz. These are two kinds of minerals. The highlight, the chemical formula is sodium chloride, which the atom arrangement is like this. And quartz is very common and sometimes very beautiful minerals in nature, which the chemical formula is silicon dioxide. So we can draw a summary of definition of mineral. A mineral is a naturally occurring in homogeneous solid with a definite chemical composition and a highly altered atomic arrangement. It is usually formed by inorganic process. It means it's not formed from animal or vegetable matter, as I said just now. And the chemical elements and the crystal forms determine the properties of the minerals. And the chemical elements depend on the composition of the rock in liquid state. And this is another mineral that everybody wants it, which is very valuable, and especially for the engagement between boyfriend and girlfriend. And it is composed by carbon atom, which is one kind of the hardest solid. So highly ordered atomic arrangement is referred to the internal structure framework of atoms, which is arranged in a regular geometric pattern. Because this is the criteria of the crystalline solid. Minerals are crystalline. And in fact, the study issues of mineralogy generally includes identification of minerals, classification of minerals, and the formation of minerals. So in this course, we put more attention on something on engineering. So we could concern soil or rock strengths mostly. And the rock, as I said, a rock is composed of minerals. So rock strength is controlled by the structure of minerals. And the major structures of minerals including cleavage, parting, and fracture. So the property of cleavage, parting, and fracture are the response of a crystalline material of external force. So, speaking of cleavage, it is a term as a description of the ability of a mineral to break along preferred plane. And the mineral tend to break along the certain planes because the bonding between atoms is weaker there. And friction, on the other hand, fracture is the way a substance breaks where not controlled by cleavage. Let's see as the two most common structure in the minerals. So cleavage is a very essential property for recognizing minerals, and it is also the origin of the cleavage formation in rocks. So it is very important property in the recognition of minerals. Crystals often contain planes of atoms along which the bonding between the atoms is weaker than along other planes. In such a case, if the mineral is struck with a hard object, it will tend to break along these planes. This property of breaking along specific plane is termed cleavage. So minerals may cleave in 1, 2, 3 or more directions. So these are some very brief introductions to the minerals. Actually, mineralogy is a very a big and deep subject. In geology and some geologists studied minerals and rocks for their lifetime. But here, we put more attention about in something engineering. So yeah, we just know some knowledge about minerals. It's okay. So next, let's move to the patronage. Patronage must be a very strange word for you. But yeah, the meaning is very simple. Patronage is a term used to denote the overall study of rocks, including petrography, the study of the description and the classification of rocks, and petrogenesis, the study of the histories and origins of rocks. So yeah, as it is simple that petrology is the subject which related all the overall study of rocks. So what are rocks? A rock is a naturally rocks exist naturally over the world, and it is a solid aggregate of mineral grades or solid naturally occurring mass composed of mineral grades, glass, altered organic matter, and combinations of these components. So different components and the yeah, composition patterns will form the very different kind of rocks. And based on the mode of origin, rock can be divided into three major basic types: igneous rock, sedimentary rock, and metamorphic rock. This is very important, and you must be know it in any time when I ask you. Uh, even in your final examination. So yeah, the first type is the igneous rock. The term igneous comes from the Latin ignis, meaning fire. So then is given to a rock formed at very high temperatures. Crystallite from a molten silicated material known as magma. What is magma? I will talk talk about it later very soon. An igneous rock formed from the melted rock that has cooled and solidified. Then when magma is a kind of molten rock, when it cools slowly, usually at depths of about thousands of meters, crystals grow from the molten liquid and a coarse-grained rock forms. And when magma cools rapidly, usually at or near the Earth's surface, the crystals are extremely small and a fine-grained rock results. So you can see the different depths when the where the magma cool and the different rates magma cools the different rock types will be formed. And magmas originate usually in the upper mantle at depths between about 50 and 250 kilometers. And the convergent plate boundaries where the oceanic crust drives deep into metal. The magmas are generated by the resulting melting. And at the mid-ocean ridge, new oceanic crust is created from material coming up from the Earth's mantle. And the molten rock below the Earth's surface that rises in volcanic vents is known as magma. This is definition of this word. But after it either will erupt from a volcano, and such a thing it's called lava. So yeah, in summary, magma is molten rock that is uh, within the beneath the ground, and the lava is the molten rock that has erupted onto the ground surface. So yeah, they are referred to the different depths and the deposition way uh, for the rock formations. So magmas form in the metal and the lower crust. They rise towards the surface because they are less dense than the surrounding rocks. And these magmas may crystallize partially or entirely at various depths in the crust, or they may crystallize at or near the surface of the Earth. In either case, the products of crystallization are igneous rocks. And natural magma are hot, which temperatures range from uh, 500 to 1200, and viscous siliceous melting which the chief elements present are silicon and oxygen, and the metal potassium, sodium, calcium, magnesium, aluminum, and iron in the order of this chemical activity. And together with this, may constituents are small amounts of many other elements and gases such as carbon dioxide, sulfur dioxide, and water. And the color deepest of mineral and rocks descend from up to down in this slide. This slide shows the Bowen's reaction series. And this Bowen's reaction series is the work of the pathologist who summarized the sequence of crystallization of common silicate minerals from a typical basaltic magma undergoing fractional crystallization. And Bowen's Bowen's reaction series really consists of three series, and it is broken in many. Generally, it is broken into two branches, and the continuous and discontinuous. And the mineral at the top of the illustration. In first to crystallize, and so the temperature gradient can be graded to be from high to low, with the high temperature minerals being on the top, and the low temperature are ones on the bottom. And the branch on the right of the illustration is a continuous one and results in progressively sodium-rich plagiarized class at lowering temperatures. And in the discontinuous series, minerals such as olivine will crystallize at a high temperature as magma cools. And however, if they are not precipitated out, the composition of the magma does not change. And as the magma further cools, the olivine will recrystallization as a proxy. And igneous rock occurred in two ways, either as intrusive bodies or as extrusive rock. The differences are one is below the surface and the other one is on the surface. So as the ultimate source of igneous magma is probably deep in the crust or in the upper part of the metal. And the terms intrusive and exclusive refer to the place where the rock solidified. So the intrusive rock is characterized by a slow cooling rate and large crystals, while the exclusive rocks has features of quick cooling rate and tiny crystals or glassy. So first let's speak of the intrusive rock, which has a name of plutonic rocks. This kind of rocks formed from the cooling and the solidification of magma deep within the crust is known as intrusive igneous rocks. And within the Earth's crust, the temperatures and the pressures are much higher than at its surface, and consequently, the hot magma cools slowly and crystallizes completely. And the slow cooling promotes the growth of minerals large enough to be identified visually without the aid of a microscope. And the rocks formed from the cooling and solidification of magma extruded onto the crust as known as uh, extrusive igneous rocks, which has another name of volcanic igneous rocks. And in such a case, the magma erupted at the surface is chilled so quickly that the individual minerals have little or no chance to grow. So as a result, the rock is either composed or of minerals that can be seen only with the aid of a microscope or contains no minerals at all. So the chemical composition of the magma from which an igneous rock is formed determines the mineral composition of the solidified product. And the high silicon content are called acidic rock. And it has a light color and relatively low specific gravity. And on conversely, the basic rock as contains lime and magnesium and iron, no silicon content. It's a kind of rocks called basic rock, and it is dark in color or green and very heavy. As the higher the larger density than the density of acidic rock. And basalt contains the least amount of silicon and erupts at the highest temperature compared to the other types of lava. It has the lowest viscosity. It moves over the ground easily. So these are the classification of igneous rock on the basis of silicon content. And the greater silicon rocks contain, the lighter color the rocks have. The rocks are arranged under the four different headings, namely acid rocks, intermediate rocks, basic rocks, and ultra basic types. And the acid type is composed of light colored rocks with dominance of quartz and subordinate feldspar. The quartz and the feldspar are very light in color. And the rocks of basic type are dark colored and contain mainly feldspar and ferromagnesia minerals, and in intermediate type contains both light and dark colored minerals and spare quartz. And the two rocks under ultra basic type are olivine olivine rich rocks. And these are some the detailed classification, sub classification of igneous rock. And so the plutonic rocks are those crystallized at some steps below the surface, like gabbro, diorite, and granite, due to the different contents of silicon. And the extrusive rocks are those formed from magmas cooled at or beneath the surface, which including the basalt, andesite, and liosnite. So, as to the texture of igneous rock, it refers to the pattern of gray arrangement. If a rock exhibits grays in the form of large crystals, it has a ferric texture. And if the crystals are not well developed, the rock is fine grade, and if the ground mass is glassy in nature, it is said to have a phanetic texture. And the arrangement of feldspar in a basaltic rock is called ophitic texture. And the texture is termed porphyry when the large crystals called phenocrysts are embedded in fire grade matrix. And the porphyry texture is generally found in rocks of hyperbyzal origin, and the snow cooling forms large grains, whereas southern cooling, as being the case of the extrusive rock, results in fine grains and glass. And some structures, such as vesicle, as seen in basalt, the characteristic features of rocks or volcanic origin. So the igneous rock has different grain sizes. The textural feature of most igneous rock is the grain size, and the size of the individual mineral crystals. Grain size is controlled by cooling rates and the rate of crystal liquidation. So in summary, rocks formed in a larger cooling rate, it will have a larger grain size. And conversely, is rocks formed in the lower cooling rate will have a small grain size. So magma usually began to crystallize slowly at depths, and then was suddenly erupted from a volcano. So that's the reason why the porphyry structure could be formed in the intrusive rock. And here, I think you need to know what is volcanism. So a volcano is a conical hill or mountain formed around an opening in the Earth's surface through which hot rock fragments, gases, and lava are injected. As the solid materials accumulate around the conduit, they build up a cone which increases in size until a huge volcanic mountain is formed. The cone so constructed is called a volcano. And the form of extrusive igneous activity that does not produce volcanic cone is that of fusion eruption. And it is kind of an eruption that lava issue quietly from non-crack in the Earth's surface with little gas emission. So when the volcanism occurred and it extrusive and intrusive igneous rocks are formed, and this figures shows different patterns of the uh, igneous rock. And the Bastonese is referred to the largest deep-seated or plutonic mass rock mass. And these are bodies of coarse grade which have very surface areas greater than 100 square kilometer. And the stalks is referred to the vertical or nearly cylindrical intrusions which have a surface area of less than 100 kilometer square kilometer. And the steel is a word describing the intrusive rock, which are rocks which are tabular shape, which are coordinate. Sorry, which are concordant with the major structure of the country rocks. And the dikes are the uh, is another way, another types of the igneous intrusive in igneous rock, and it is tabular of steeply inclined with cut across structure of country rock, and the length of it in outcrop may vary from meters to kilometers, and dikes may also occur in forms as a ring dike and as a core sheet. And veins are the smaller injection of igneous rock materials, and they are often thin and irregular. Okay, these are all the knowledge about the igneous rock. So next, let's move to the most common rocks, sedimentary rock. Sedimentary rock form at and near the Earth's surface from sediments, which including the unsolidated accumulations of rock, mineral grains, and organic matter that have been transported and deposited by wind, water, or ice. So when the sediments become consolidated into a cohesive mass, they become sedimentary rock. After a very long-term rock formation history. And most sedimentary rocks become cemented together by minerals and chemicals after the formation history of about millions of years. So in the beginning, the loosened consolidated debris, for example, you can see in this figure, we can pay attention of the actual or process of forming or accumulating sediment in the layers, and also for the alluvial fan. Yeah, it is a very typical loosened consolidated debris, and after millions of years later, they become consolidated into a cohesive mass, and after that, they will become sedimentary rock. So in sedimentary rock, the stratification is the most obvious feature of the sedimentary rocks, and the layers are visible because of differences in the color or texture of adjacent beds, straight thicker than 1 centimeter are commonly referred to as a bed. So you can imagine that hundreds of years ago, yeah, this deposit is beneath the water in the river, and um, the materials will deposited layers on layers. So after a long history, yeah, they consolidated and become a sedimentary rock, and formed like this with such horizontal structures. And thickness layers are called laminations or laminate. The upper and lower surface of these layers are called bedding planes. This is the bedding planes. This is very important that almost all kinds of materials for engineering, like some building dam foundation, or some the slope, the orientation of the bedding plan is very important for the stability of infrastructure. The process of sedimentation included four stages are as follow. The weathering of the including the weathering of the outer rock, transportation by rain, rain river activity, sea move, glacier, and the deposition of in lower land, and finally the nidification. And the outer rock, uh, yes, the refer to the pre-existing rocks were weathered due to the physical, chemical, or biological weathering, and the rocks decomposed and become small fragments. You can see like this. And transportation is a process that the rocky fragments were moved from high land to lower land, based on by rain, river activity, wind blow, glacier, and sea move separation will be completed in this stage. And all weathered material and fragments must deplete in no ground, flat country, basin or sea, and form soft sediments. So the all sediments subjected to pressure or cemented together, lixiviated, hardened to sedimentary rock, and this process is related to the consolidation and lixification. And according to the way they were formed, sedimentary rocks can be classified as marine, extreme deposits. Extreme yes means lake deposited, which are usually formed by the blockage made by landslides, and glacier, aeolian, the wind deposit, deposits and fluvial deposit and the fluvial deposits, and they can be classified by their mode of orange as clastic and chemical precipitation or organic. The classic sedimentary rocks are composed of rock fragments or mineral grains broken from adding types of pre-existing rocks, and they are subdivided according to fragment size, and commonly size are mixed, requiring intermediate names such as sandy silt stones. Like the gravel with grain size larger than 2 millimeter will be formed as a conglomerate or breccia under the compaction or cementation, and the sand with a grain size between the uh, yeah the 0.062 millimeter to 2 millimeter will become sandstone, and the silt and the clay will become the siltstone and the shale under compaction and cementation. And this are the detailed classification of sediments and sedimentary rocks. And I think you can read it, see it by yourself. And the non-clastic sedimentary rocks are formed by chemical precipitation, by, for example, the biologic precipitation, and by accumulation of organic materials. And the rocks are classified mainly by composition. So, as with the clastic rocks, these rocks commonly mix both among themselves and with the clastic rocks. And these are some common rocks, including carbonate, membrite, chert, and organic process. And in such processes, and the limestone, dolomite, and gypsum, silicon, and coal will be formed eventually. And limestone, is one of the sedimentary rocks. It can be distinguished by the presence of fossils, and it will effervesce bubble quickly when dilute hydrochloric acid is applied to it. So it is a very important way for identification for the identification of the limestone when we work in the field. And marble is a crystalline form of limestone, and generally distinguished by its crystalline texture, but always effervescent when treated into dilute hydrochloric acid. And the dolomitic limestone is generally dark in color, and it bubble slowly when treated with cold hydrochloric acid. And actually, the bubble is not a kind of sedimentary rock. Instead, it is attributable to the metamorphic rock from transformed from the limestone. Okay. Okay, in fact, the sedimentary rocks has the four levels of structures. First is the bedding is referred to layers of 1 centimeter to several meters in thickness. The limitation is means layers of less than 1 centimeter in thickness. And the cross bedding is inclined. You refer to the inclined stratification of the bed, graded bedding is the decreasing grain size from the bottom or of the top of the bed. Yeah, you can imagine when the deposits happened, the river or the movement of water will be slowed down, right? And so the greater the larger size grains will sit it under the smaller size grain. And the difference in character of sediments or sedimentary rock may result from firstly the variation in currents and secondly the seasonal change and the climatic change and fluctuations of sea level. The bathing is very important and very common, and it is referred to the arrangement of a sedimentary rock in bed or layers of varying thickness and character. The general physical and structural character or pattern of the beds and their contents within a rock mass, such as gradient bedding and cross bedding. These are some the thinner layers of sedimentary rock, which we call it lamination, and it occurred often in alternating bed between the some sandy layers and clay layers. The gradient bedding is characterized by a regular change in grain size within a single bed from coarse, like I said, at the bottom and to fine at the top. Yeah, you can see this figure, and you can imagine that there are at least four stage of floods. For example, at first the river moved this deposits, and when the river rate, the water, the moving rate of the water slowed down, the coarser grains will deposit firstly earlier, and after that the smaller and the smallest grain size the grain uh, deposit on the top. And after that, another stage of flood happened, so which moved the coarser grains on the over the previous deposit again. So yes, it is exhibited like this. And cross stratification is a general term for the internal bedding structure produced in sand by moving wind or water. If the individual inclined layers are thicker than 1 centimeter, the cross stratification may be referred to as cross bedding, and a thinner inclined layer is called cross lamination planes. And many sedimentary rocks contain the remains of ancient life known as fossils. Animal tracks produce pits on the sedimentary surface by the animal tracks or on soft mud, for example, the dinosaur footprint or the fossil fish. Yeah, you can imagine when the dinosaurs walked through the soft sedimentary or mud, the ground occasionally hardened quickly enough to preserve their footprint. Okay, the last type of rock is metamorphic rock. The term metamorphism is derived from the Latin for change of form. And the metamorphic rocks are created by changes induced by at high temperature or high pressure, and these changes take place in solid state. So the two most common agents of metamorphism are heat and pressure. And sometimes rocks are subjected to pressure too intense or heat so high that they are completely changed. They become metamorphic rocks, which form while deeply buried within the Earth's crust. And the process of metamorphism does not melt the rocks, but instead transforms them into denser, more compact rocks. New minerals are created during this process either by rearrangement of mineral components or by reactions with fluids that enter the rocks. And pressure or temperature can even change previously metamorphism metamorphosed rocks into new types. So metamorphic reaction occur because all minerals are stable only within certain ranges of temperature and pressure. If temperature or pressure rises above the level at which a mineral is stable, it will decompose and its components will recombine to form a new mineral that is stable at the new condition. So the process is called metamorphism. It is a name given to the process of processes by which the mineralogy and texture of a pre-existing rock is changed. A rock may have originally been igneous or sedimentary or even a previous metamorphism rock before being subjected to a change in physical conditions such that the mineralogy to or texture is altered. So the point is that metamorphic process indicates that the mineral and structures in igneous rock or sedimentary rock is changed due to the high temperature and um, high pressure. So the parent rock of metamorphic rock could be either igneous rock and sedimentary rock. The main agents of metamorphism are therefore the temperatures, pressure, stress, and the chemical activity, and metamorphism is due to the effects of one or more of these factors. Yeah, it is easy to understand that the deeper the location is at, the higher temperature it is. And in this figure, the yellow colors, the rock with yellow color refer to the sedimentary rock, which we can clearly see the bedding. And by the way, do you remember the biggest difference between the sedimentary rock and igneous rock structures? Yeah, the answer is that the sedimentary rock have apparent bedding plans, structures, or lamination, while the igneous rock is really massive rock. Is that right? So this figure shows the contact metamorphism. It is one kind of metamorphism process. The contact metamorphism involves high temperature only that occurs in metamorphic uh, arrows, each from 1 meter to 2 kilometer wide, around the igneous intrusions where rock has been baked. And the most important agent of metamorphism is temperature, because it provides the energy to drive the chemical exchange that result in the recrystallization of minerals. Like I talked, it means the process that the original mineral decomposes and the components recombine to form a new mineral that is stable at the new condition. And the magma and its fluids react with the wall rock and the groundwater and replace wall rock with raw minerals. And under intense heat, the mineral of existing rocks begin to recrystallize to form a new mineral. Deformation usually does not occur, so the rocks commonly show no foliation. And such kind of metamorphic rocks commonly show no foliation. The foliation refers to the thin layer in metamorphic rocks as a result of the flattering and the stretching of mineral grains during a metamorphism. And the original metamorphism is one more type of metamorphism, and it takes place in active sequence of crust, particularly in mobile melts, where both strong stresses and unusual high temperature prevail. And such kind of metamorphism involves high temperature and pressure. It occurs in mountain chains due to continental collision on plate boundaries, for example, and it extends over large areas. And the foliation are formed during its process. It's very similar to the bedding plans of sedimentary rock, but they have a totally different formation way. And the hydrothermal metamorphism is a special kind of metamorphism in which new chemical compounds are added by hot iron-rich solutions. So it involves hot water rising from below, coming from a volcanic source. And this metamorphic process causes many changes in rocks, including the increased density, the growth of larger crystals, reorientation of the mineral grains into a layered or banded texture, and the transformation of low temperature minerals into high temperature minerals. And this is the classification of metamorphic grade for different metamorphic rock. And the metamorphic grade is the overall extent of change, notably in the sequence from slate to schist to gneiss. And the depths increase from up to down along the vertical direction, and the temperatures increase from left to right along the horizontal direction. So, yeah, please understand this slide by yourself after this class. And for classification and identification, metamorphic rocks can be subdivided into two textural groups: the foliated rock and non-foliated rock. Yeah, the foliated metamorphic rock rocks have directional or layered aspect, like which are similar to the bed plans or sedimentary rocks. And the non-foliated rocks are homogeneous or massive rocks, where this kind of rocks are usually originated uh, from the granite or some other igneous rock, which is has no bed plans, and instead they are massive rocks. And these two types of due to foliation conditions contains different rocks. The foliated rocks mainly involved shale, slate, finite, schist, and gneiss, which are attributable to regional metamorphism. And the non-foliated rocks are usually formed by the thermal or contact metamorphism, like the marble originated from limestone. And although they are called non-foliated rock, but we could still recognize the original bed plans because the original rocks are sedimentary rock, especially for the marble. So this is related to the very important process, recrystallization. Rearrangement of crystal structure of existing minerals is referred to this term. And commonly, many small crystals merge to form larger crystals, such as the clay in shale, becoming micas in state finite and schist. No change in overall chemistry. And new crystals grow from the minerals already present. A preferred orientation of minerals develops under applied pressure. Platinum or sheet-like minerals such as muscovite and biotite become oriented perpendicular to the direction of force. Then this preferred orientation is called foliation. As I said just now. The foliation is really parallel arrangement of minerals, and it's referred to the thin layer in metamorphic rocks as a result of the flattering or stretching of mineral grains during metamorphism. And some other kinds of structures in metamorphism are shown here. And the schistosity is parallel arrangement of micas or some other platinum minerals. The static cleavage is referred to the structure that describes the parallel arrangement of very fine grade micas in a slate. And from them the nicosity is the word is term that examines the alternation of lighter and dark layers as in gneiss. And it is notable that the equidimensional grains such as quartz or calcite, there is no preferred orientation for them, and the grains form a mosaic, like you can see in this figure. So here, we show the summary of rock characteristics, and for the three major rock types, you need to remember them very familiarly. So in summary, in this learning segment on minerals and rocks, you should grasp the point that there are three main types of rocks, which are igneous rock, sedimentary rock, metamorphic rock. And for the igneous rocks, they are formed during the melting of rocks in hot, deep crust and the upper mantle. And the forming process is mainly about the crystallization and solidification of magma. And the sedimentary rock consists of fragmental deposition, burial, and nidification. They are characterized by developed bedding plants or lamination. And the metamorphic rocks are evolved from the igneous or sedimentary rocks under high temperatures and pressures in deep crust and upper mantle. And they are usually affected by um, tectonic activity and develop foliation besides the original geologic structure. The point of the forming process is recrystallization in a slight state of new mineral. Yeah, please read it by yourself. Right. Actually, in our original plan, we will have a very interesting class for the minerals and rocks identifications. And but unfortunately, we can only have this class online, so we cannot enter the uh, laboratory in our college. So I can only show you some very interesting videos to see how the minerals and rocks looks like.
Hello, Fleming College. We have a rock and mineral ID test coming up. We've got 40 rocks and minerals on there, 21 minerals and 19 rocks. So let's get down to business. Start off with our minerals. Quartz. Quartz has a hardness of 7 and is the hardest mineral in this set. The luster is glassy, non-metallic, but be careful because quartz can be almost any color. It has conchoidal fracture, no cleavage, but is sometimes in crystal form. It has sharp edges and is a common rock-forming mineral. Calcite has a hardness of 3 and can be scratched with a knife. Its luster is vitreous to earthy and non-metallic. It has good cleavage and is rhombic. It can be many different colors and effervesces with a dilute 10% HCl. Plagioclase has a hardness of 6 and a non-metallic luster. It streaks white and has good cleavage at right angles and twinning striations. It's usually light in color, white or gray. Orthoclase. The hardness of 6. Its luster is non-metallic, vitreous. It streaks white. It has good cleavage at 90 degrees. The color is most often light to medium red, but can be white, gray, or green. Biotite and muscovite. With a hardness of 2.5 to 3, it's very soft. Its luster is non-metallic. Perfect basal cleavage, splits off easily into thin sheets that are elastic or plastic. The color is opaque to translucent. Biotite is always black. Muscovite is brown, light green, or beige. Hornblende. With a hardness of 5.5, it's as hard as a knife. Its luster is vitreous and non-metallic. It has a bright black, splintery appearance. Its cleavage, not always easy to see, angles 56 degrees and 124 degrees. The color is black to dark green or brown. Pyroxene. Hardness of 5.5, same hardness as a knife blade. The luster is vitreous to glassy and non-metallic. The color is light to medium, gray or green. It has visible cleavage planes at approximately 90 degrees. Talc, with a hardness of 1, is very soft and can be scratched with a fingernail. The cleavage is perfect basal, the streak is white, the luster is pearly to greasy, non-metallic, silky appearance, slippery to the touch. The color is pale green, white, yellow, or translucent. Pyrite. Hardness of 6 to 6.5, it's harder than a knife blade. The luster is metallic, has no cleavage, and is massive. The streak is greenish or brownish black. The color is opaque, pale brass yellow, sometimes called fool's gold, and is harder than chalcopyrite. Chalcopyrite. Its hardness is 3.5 to 4, softer than a knife blade. It has no cleavage and is massive. The luster is metallic. The streak is greenish black, softer than pyrite. The color is brassy to greenish yellow. Graphite. With a hardness of 1 to 2. Its luster is metallic to dull. The cleavage is perfect basal. The streak is black and it marks paper. Has a greasy appearance and feel. The color is black to steel gray. Hematite. The hardness of 5.5 to 6.5. The luster is mostly non-metallic, found in compact red earthy masses, but can also be metallic, dull silver. The streak is always red. Red powder will come off in your hands. The colors are red, reddish brown, black, or metallic steel gray. Magnetite. With a hardness of 6, it can't be scratched with a knife. Its luster is submetallic, dull metal appearance. There is no cleavage and it is massive. The streak is black. It is magnetic and will affect the compass. The color is iron black. Gypsum. With a hardness of 2, it scratches easily with a fingernail. Luster is non-metallic, clear crystalline form called selenite, compact variety called alabaster, most often in massive form. Color, usually white, also gray, reddish, or brown. Serpentine, with a hardness of 2.5 to 4. Cleavage is not prominent, conchoidal fractures. Luster is non-metallic, greasy to waxy. Texture often has greasy or slippery feel, and the color is most often green. Barite, the hardness of 2.5 to 3.5. The luster is non-metallic, vitreous, often transparent or translucent. The streak is white. The cleavage is perfect basal and prismatic, or could be massive with fractures. Specific gravity, 4.3 to 4.6. Occurs in tabular crystals, in granular form, or in compact masses resembling marble. Color, it's colorless to white, yellow, brown, red, green, or black. Chrysotile, hardness of 2.5 to 4. The texture, it has flexible fibers which are easily separated. The luster is non-metallic and silky. Colors can be green, white, yellow, or brown. Galena, hardness of 2.5. The luster is metallic. The specific gravity of 7.6. The streak is medium gray and colors are medium to dark gray. The cleavage is parallel to crystal cube faces. Pyrrhotite, with a hardness of 3.5 to 4.5, the streak is grayish black. It has no cleavage and a specific gravity of 4.6. It may be yellow to bronze in color and tarnishes to iridescent colors. And it may be magnetic and the luster is metallic. Sphalerite, with a hardness of 3.5 to 4, the luster can be black, variety metallic, or other common colors that are non-metallic. It has cleavage with a specific gravity to 3.9 to 4. The streak is brown. Colors can be yellow, brown, red, or black if iron is present. All right, that'll do the minerals. Now let's get into the rocks. I'm going to start off with granite. Its texture is haneritic, medium to coarse grained. The structure is massive. The color is white to gray, mostly pink. The hardness is greater than 5.5. Its composition is made up of quartz, orthoclase, plagioclase, biotite, and hornblende. Basalt. Texture is aphanitic, fine-grained. Structure is massive, vascular, hemictyloidal, flow, pillows, ropey, blocky, or columnar. The color is dark gray to black. The hardness is greater than 5 to 6. Its composition consists of plagioclase, pyroxene, olivine, and some hornblende and biotite. Limestone. Texture is calcareous, coarse-grained. The structure is characteristically thick-bedded to massive, may contain fossils, particularly in the cement. The color is variable. The hardness is between 3 and 4. The composition, it must consist of 50% or more of calcite. Shale. Texture is fine-grained. Structure is laminated, splits into thin plates, may contain fossils. Colors are light to dark gray. Iron oxides may give brown and red colors, which are dull. The hardness is soft, easily scratched and weathered, may disintegrate in humid climates. Its composition consists of silt and clay-sized particles and clay minerals. Gneiss. The texture is uneven, granular, medium to coarse-grained, crystalline. Structure. Gneissic banding, parallel mineral orientation, alternating light and dark bands. Color is light granular layers and dark foliated bands. The hardness, granular layers 6 to 7, foliated layers 2.5 to 3. Its composition consists of orthoclase, quartz, biotite, hornblende, and it is named for parent rock. Marble. Texture is even and granular, fine to medium grained, calcite crystals. The structure is massive. The color is white, but accessory minerals will color the rock. The hardness is 3, is easily scratched and easily eroded. It consists of calcite or dolomite. Rhyolite. Texture is aphanitic, maybe porphyritidic, medium to coarse grained. The structure is massive. Color is light gray, yellow, and red. The hardness is 6 to 6.5. The composition consists of quartz, sanidine, feldspar, biotite, and hornblende. Andesite. Texture is aphanitic, maybe porphyritidic, fine-grained. The structure is massive. Color is brown, green, and dark gray. Hardness is 5 to 6, and its composition consists of plagioclase, hornblende, pyroxene, and biotite. Diorite. Texture is phaneritic, coarse-grained. Structure is massive. Color is light to dark gray. Hardness is 5.5 to 6. The composition consists of greater than 10% of quartz with orthioclase, plagioclase, hornblende, and biotite. Gabbro. Texture is phaneritic. It's coarse-grained. The structure is massive. The color is dark gray or greenish black. The hardness is greater than 5.5, and the composition consists of plagioclase, pyroxene, hornblende, and olivine. Porphyry. The texture is porphyritic. It has coarse crystals. It's a light color matrix. The background is fine-grained and dark color. The color varies. The hardness is greater than 5.5, usually picked from the individual mineral. The composition varies. Nepheline syenite. Texture is phaneritic and coarse-grained. Structure: it has poor cleavage, is translucent with greasy to glassy luster. The colors can be white, yellow, gray, green, or even reddish or pink. The hardness is around 5.5 to 6. The composition consists of sodalite, apatite, pyroxene, sphene, and feldspar. Limestone. Texture: calcareous rock, fine-grained, composed mainly of the mineral calcite. The structure: stratification usually indistinct, sometimes fossils present on surface of rock. Color is variable. The hardness is 3 to 4. Dense varieties break with a conchoidal fracture. It must consist of 50% or more of calcite. Dolomite. Texture is coarse to fine-grained. Structure is massive. Color is white, colorless, buff, brown, pink, or gray. Hardness is 3 to 4. Effervesces very slowly in cold hydrochloric acid. Sandstone. Texture: even granular sand size. Structure is massive, bedded, cross-bedding, and ripple marks. Color varies depending on cement: white, tan, brown, red, or green. Hardness varies depending on cementing materials: quartz, grains. The composition consists of quartz grains, if feldspar grains called arkose, silica, carbonates, clay, or iron oxides as cementing agents. Talc schist. Texture is medium to coarse grained, talc feel, and flakiness. Structure: schistose foliation, parallel alignment of flaky minerals make more than 50%. Color is silvery white, gray, yellow to brown, tones from iron oxides. Hardness and ease of splitting depends on micaceous minerals present. It's usually soft, 1 to 3. The composition consists of the name for foliation producing minerals which are present: micas, muscovite, chlorite, talc, and hornblende. Slate. Texture is dense and fine-grained. Structure is slaty foliation, thinner layers, parallel alignment of mica, flakes, no fossils. Color is usually medium to dark gray or black, green, purple, red, brown, and shiny luster. The hardness is easily scratched with a knife and it is brittle. Its parent rocks are shale or mudstone. Quartzite. Texture is even granular, fine to medium grained, sugary. Structure: massive, thick bedded, outlined of original grains imperceptible. color is white when pure, light to dark gray, or brownish to pink from accessory minerals. Hardness is 7, tough but brittle with splintery fractures. The parent rock is quartz-rich sandstones, grains, and cement. Muscovite schist. The texture is medium to coarse grained with a talc-like feel and flakiness. The structure is a schistose foliation, parallel alignment of flaky minerals make up 50%. The color is silvery, white, gray, yellow with brown tones from iron oxides. Hardness and ease of splitting depend on micaceous minerals present, which are soft, from 1 to 3. The composition named according to the most conspicuous foliating producing mineral in the rock.
Alright, this is today's class. Listen here. Okay. See you tomorrow, guys.